Hello, this is Stephanie Lansing, and I'm talking today about food waste diversion and anaerobic digestion as pillars in a resilient bioeconomy. And I have many co-authors helping me with this work. So, in the foundations of a circular bioeconomy is that we create resources and food to meet people's nutritional needs, energy, and personal needs while mitigating climate change, providing renewable resources, reducing wasted food, and that creates these local circular systems. This creates benefits to both people and nature, which is the foundations of a circular bioeconomy. When we think about wasted food, about 40% of all global food produced is wasted. It doesn't go to feed people. This food waste accounts for about 10% of global greenhouse gas emissions, and one third of food of landfill content in the US is food waste. This impact of food waste is both environmental, social, and economic. And in reality, this wasted food should be used to feed people. 20% of all children in Prince George's County, where the University of Maryland is located, experience some food insecurity. So at NourishNet, this is a food recovery toolbox that we've created to help put healthy food in the hands of the food insecure. I'm the PI of this NSF grant that's part of the Food and Nutrition Security Convergence Program. So at NourishNet, we know that there's 13.5 million people without access to fresh food. And so Food Loops is an app that we've developed that coordinates food access, donations, and data. In this Food Loops app, someone like Arlene can look at the app to see when the distribution events are, what the available foods are. But if their apples are not available, she can send a wish list that will give her a notification to let her know where this is located. So we currently have this in English and Spanish with a mapping function to help you find out where is the easiest place to get the food that you need. And also some data collection, which is non-identifying, to help us know where food is needed, where people are accessing data. And we've been currently beta testing this in English and Spanish with food insecure end users. We also know that there's 63,000 grocery stores that can't verify the freshness of food to donate. And so we've created a quantum nose, which determines the safety of food, including donated food. And a quantum knows there's no more guessing. It's a personal food freshness sensor. So instead of me saying, can you smell this meat and see what you think? What the quantum nose does is it takes gas molecules from bacteria on spoiled food and it detects if those molecules are present and the concentration of those molecules. So it allows us to know the safety of the food. Is it contaminated or not? And is it safe to donate? We also know, as we said, that 33% of the food in the US is wasted, which is 3% of our greenhouse gases produced. And so at Food Loops, we're providing a platform for real-time resiliency data. This would allow someone like Mayor Hollingsworth to understand where she needs to put infrastructure, whether it be donation sites or composting and digestion for spoiled food. It provides real-time data on greenhouse gas reductions from these decisions to inform infrastructure in her city. For example, we have done some case studies that showed at one pantry, Linda Bean Foundation, they rescued 73,000 pounds of surplus food every year and provided that to food insecure individuals, providing over 100,000 meals a year. And that is the equivalent of avoiding 49 tons of CO2 emissions because that food did not go to the landfill, which is equivalent to the CO2 reduction from electricity from 1,000 solar panels. So again, just from these 5 places they rescued food from, they were able to rescue 3,000 food and reduce over 2,000 pounds of CO2 equivalents. So at NourishNet, we're really providing an end-to-end holistic solution across the entire food ecosystem. So we're bringing consumers into this space, coupling it with our sensor to help facilitate those connections between people that are at the grocery stores and at the pantries to make sure that they know the verification of the freshness of the food, the reliability of that food, and their ability to serve that food to individuals that need it. And then providing real-time data to make infrastructure decisions. In our lab, I run the bioenergy and biotechnology lab, and it focuses on the unrecoverable wasted food, which we want to be the smallest portion, right? So this is the spoiled food that we can't, or for whatever reason, we can't bring it to individuals. It may be food processing waste, it may be manure, it may be other waste that can't be used to feed people. So we determine the best avenue for turning this waste into value and try to incentivize collection and reduce greenhouse gases from waste emission. So what is anaerobic digestion? So we put the waste into a sealed container, which creates biogas. That biogas can be used for renewable electricity, for driving cars, for heating. And then we separate out the solids. So the food waste, if it's going into the digester, now we separate out the solids after digestion. We can sell a composted product for the solids as cells, but then also the liquid part of that waste goes directly on the crops for fertilizer. So really anaerobic digestion can be a pillar in circular economy where we have greenhouse gas reductions, renewable energy, and food production from the nutrients that are already in these waste products. So the benefits of anaerobic digestion, it's non-intermittent. It's 7 days a week, 24 hours a day. And then what the biogas that's produced can be used in such a variety of manners. It can be used for heat, electricity, renewable natural gas. The waste heat from the combined heat and power generation can also be captured to heat the digester itself. It reduces methane and CO2 emissions that would be released into the atmosphere, processes food waste and power, produces power from waste that would go to the landfill, and then creates fertilizer from that waste so the nutrients from the food can be used to grow more food. So, for example, here is a success story of a heated covered lagoon digester that treated both dairy manure and food processing waste in Maryland. And so we did a life cycle assessment of this digestion system. And we found that the 1.8 million meter cubed of biogas that was produced per year resulted in 2,000 megawatts of electricity, which is enough power for 190 homes in the US. The effluent was used to land apply to grow more crops. They actually did solid separation prior to digestion. So the solids from the manure actually was used for composting and sold separately. And all of this process resulted in 2,000 tons of CO2 emissions avoided per year, which is the equivalent of taking 4,000 cars off the road each year. So there's also a lot of energy that can be created here at the university. When I flush my toilet, it goes to the DC wastewater treatment plant. And DC water actually has thermal hydrolysis, kind of like a pressure cooker before the digester. And the waste from the sewage sludge is enough to power 10 million megawatts of power, enough to create 10 million megawatts of electricity, which powers 8,000 homes, all through implementing this digestion process. In Maryland, there's also the Bioenergy Center that processes over 100,000 tons of pre-consumer food waste. And so this produces 300,000 megatons of renewable natural gas. They scrub out the CO2 to go to renewable natural gas. And then the separated solids after digestion are sold as compost. The liquids, because it's in a very urban area, actually end up going to wastewater treatment. So they aren't used on the fields because they're too far away to transport. So when we think about the EPA, first they want us to, their wasted food scale, they want us to prevent food waste. If we do have the food waste, donate it or upcycle it, feed animals or leave it unharvested on the field, compost or digestion, making sure that we use the effluent to go back on the field to grow more crops. Anaerobic digestion, where you dispose of some of it, like going back to wastewater treatment plants, is a little bit less preferred. And finally, we don't want to send it down the drain, landfill, or incinerate. So one of the questions that we had in our lab is how much energy can we make from trash? And so we want to incentivize this food waste collection. As we said, most of our trash is food. And so we want the good source separation compared to the poor source separation. And so we're sorting and mapping trash from restaurants, schools, universities, grocery stores, landfills, all around the US, and showing incentives for the circular economy. The idea is we sort the waste, the MSW, the municipal solid waste. The high moisture fraction goes through solid state anaerobic digestion. The low moisture fraction, so this is things like plastics and fibers and papers, go through gasification. Then we have the syngrass coming together, Fischer-Tropsch synthesis to create sustainable aviation fuel. All of this is followed with technical and economic analysis, lab scale testing and validation of this characterization to produce a characterization map to really understand the food waste across the landscape. And what we can see is that most of the food waste is here in the grocery store and the restaurants. In the schools, we also have food waste, but we have more paper, still using paper for worksheets. But then once it goes to the landfill, it gets more commingled. So really this shows the incentive of collecting this so that we can get the highest energy production at the source before it gets to the landfill, because a lot of that food kind of degrades and gets soupy and is unrecoverable by the time it gets to the landfill. When we think about the food waste itself, we actually did studies to see what food waste actually had the highest um, energy content. And what we found is that the dairy actually has the highest energy content due to the fat and protein. And the yard waste, which is also part of this high moisture waste that we see in the trash, had the lowest due to the high lignin value. But really, the fruits and vegetables, the meat, they were all very similar and they're all very high, a lot of energy that can be recovered. We're also investigating dark fermentation of food waste. So again, during the digestion process, we break up these carbohydrates to amino acids and sugars and then down to volatile fatty acids. And then during traditional anaerobic digestion, those fatty acids are used by methanogens to make methane, which in a landfill where it goes up into the atmosphere is not good. In a closed digester, that methane is what's used for energy. In fermentation, we actually block this methanogenesis process. So instead, we take these, we have fermenters, and we take it and we just produce those small acids. And then what we do is during the dark fermentation, those small acids are produced to a single cell organism. We feed them to the Haliopharix mediterranea organism, which builds up lipids inside of its cell. We extract those lipids, and if you see, we can make bioplastics here. So this is a thin film bioplastic. You can like line a paper cup, for example, and it'll degrade and doesn't have a bad effects on the environment, isn't made from fossil fuels. And so with this, we're really trying to valorize food waste. Can the bioplastic production process? So we're optimizing that fermentation, optimizing the volatile fatty acid production, looking at time, salinity, temperature, extracting it, again, giving it to that halophilic culture, salt-loving culture, recovering the salt, and seeing how much money and greenhouse gases we can reduce from this bioplastic production. And so what we've seen is that in methane, about 100%, if you add 100 grams of carbon, about 37 of it goes into methane. But through this dark fermentation, we're actually able to get 56 carbon conversion efficiency. So more of the carbon is going into a useful product, which displaced anywhere from 5 to 1 kilogram of CO2 equivalents in this product that we produce. So creating a value-added product while reducing the impact on the environment. I'm just going to briefly mention, we also have a project on microbial fuel cells. We're actually collecting marine organic matter. We're fermenting this marine organic matter and then microscopic marine organic matter. And then after it goes through those fermenters, those same volatile fatty acids, instead of making bioplastics, we're actually putting it to an MFC and doing direct electron production in the ocean. So the take-home message are really thinking about a circular system. It takes potential waste, creates local food, fertilizer products, and renewable energy. Biological-based technologies can create bioenergy, bioplastics, and reduce greenhouse gases. And a circular economy provides safe and nutritional food, a cleaner environment, renewable and resources, and less weight. And throughout all of these processes, we're always modeling the positive economic and environmental impacts of the circular economy because we want to incentivize the redistribution of waste, create resources, and incentivize using technologies such as food loops, quantum nodes, fermenters, and digestion systems. So I appreciate your time. Thank you.